Imagine getting to London in 3 hours.
That's the promise behind this jet here, the Boom Overture.
Supersonic travel could be especially important for industries involved in medical transportation and disaster relief.
Picture this. A small, unmanned aircraft rolls down a runway in the New Mexico desert. It looks almost ordinary, shaped like a scaled-down fighter jet. But the engineers watching it aren't tracking an ordinary flight. They're watching a machine that, according to nearly every rule aerospace engineers have followed for the last 50 years, shouldn't be able to do what it's about to do. It lifts off, climbs, and pushes past the sound barrier. Then it lands. And the team gets ready to fly it again next week. That single fact, fly it again next week, is the whole story. Because building something that goes fast has never really been the hard part. Building something that goes fast, comes home, and does it again tomorrow is the problem that has broken program after program for half a century. This is the story of the company trying to solve it, and why the machine they've built is starting to look like the real successor to the State Route 71 Blackbird. For nearly 50 years, one aircraft has owned the title of the fastest air-breathing jet ever flown. The State Route 71 Blackbird, a black titanium spy plane built by Lockheed's Skunk Works in the 1960s, could cruise above Mach 3, faster than 3 times the speed of sound. It was so fast that in its operational history, adversaries reportedly fired thousands of missiles at it, and not one ever connected. The Blackbird simply outran them. When it was finally retired in the late 1990s, it left behind a speed record that nobody in aviation has matched since. Concorde, the famous supersonic airliner, proved that paying passengers would tolerate a cramped cabin and a steep ticket price for a shorter flight. It could cross the Atlantic in well under 4 hours. But Concorde never got close to the Blackbird speed, burned fuel at a punishing rate, and was retired in 2003 after a fatal crash outside Paris. Between those two aircraft, the world quietly accepted a ceiling. Military spy planes could go extremely fast for short bursts, and commercial jets could go moderately fast if passengers were willing to pay for it. Nothing could do both sustained extreme speed in a reusable aircraft on a normal schedule. The obstacle was never simply going faster. It was surviving the heat that comes with it. When a spacecraft re-enters the atmosphere, it experiences enormous heat, but only briefly, and the entire vehicle is designed around slowing down as fast as possible. A hypersonic aircraft faces the opposite challenge. It has to accelerate to extreme speed and then hold it there for an extended stretch, all while carrying fuel, sensitive electronics, and eventually passengers. At those speeds, air doesn't behave the way it does at highway speeds or even at normal jet cruising altitude. It compresses so violently against the leading edges of the aircraft that it heats up before it even touches the metal. On the sharpest surfaces, temperatures at Mach 5 can climb past 1,000 degrees Fahrenheit, hot enough to soften aluminum, weaken titanium, and destroy standard fuel lines and electronics. Engineers who have spent their careers on high-speed flight tend to agree on one thing. This was never fundamentally a speed problem. It's a heat problem. And it's the reason nearly every serious hypersonic aircraft program of the last several decades either got shelved, ran out of funding, or never left the design phase. The company chasing this problem is Hermeus, a defense aviation startup founded in Atlanta by a team of engineers with backgrounds at the U.S. Air Force, SpaceX, and Blue Origin. Rather than treating extreme speed as an unsolved mystery, they treated it as an engineering problem with an engineering solution, and built their entire approach around iterating on real hardware instead of running years of paper studies. Their central bet was that no single existing engine type could get an aircraft from a standstill on a runway all the way to hypersonic cruise. A conventional turbine engine, the kind that powers airliners and fighter jets, works beautifully from takeoff through moderate supersonic speeds, but its spinning components become a liability once airflow gets hot and violent enough. A ramjet, on the other hand, has no moving parts at all. It's essentially a shaped tube that relies on the aircraft's own speed to compress incoming air. It's extraordinarily efficient at high speed, but it produces almost no thrust when the aircraft is slow. You cannot take off with a ramjet alone. Hermeus's answer is an engine they call Chimera, which behaves like a normal turbine engine at low speed and then transitions mid-flight into ramjet mode as the aircraft accelerates. The hardest moment in that whole sequence is the handoff itself, sometimes called the point where neither system has full control of the airflow. Get it wrong, and the aircraft can lose thrust catastrophically at exactly the moment it can least afford to. Hermes spent months running that transition on the ground at a university turbomachinery lab before ever trying it in the sky. And by their account, they got a repeatable, controlled handoff working in under 2 years, remarkably fast by the standards of defense engine development, which often spans decades. The current generation of the engine pairs a proven military turbine core, the Pratt & Whitney F100, the same family of engine that has powered F-15s and F-16s for around 50 years, with a device called a precooler. At high speed, the air entering the intake is already scorching hot before it's even compressed, hot enough to warp or destroy a standard turbine if it were fed indirectly. The precooler is a dense heat exchanger packed with thousands of tiny channels that strips heat out of that incoming air in a fraction of a second before it reaches the engine's core. That cooling doesn't just protect the hardware. It lets the turbine run efficiently at higher speeds than it was ever originally designed for, which narrows that dangerous handoff window between turbine and ramjet modes. Hermes has been testing this combined system at its own facility in Jacksonville, Florida, built inside decommissioned Navy test cells that date back to the mid-20th century. Owning the test site outright lets the team run their own testing schedule and swap hardware between attempts, rather than waiting in line for shared government facilities, and the company has been open about its philosophy. Build it, test it, break it, fix it, and do that loop as many times as it takes. Rather than attempting to leap straight to a Mach 5 aircraft, Hermes built a structured series of test vehicles under the name Quarterhorse, each one designed to prove a specific piece of the puzzle before handing the lessons to the next design. It began with a non-flying structural mock-up used to iron out wiring, fuel systems, and landing gear issues early, when problems are still cheap to fix. Then came the first aircraft actually built to fly, a small, unmanned demonstrator with a sharply swept wing, tested at Edwards Air Force Base in California, historically the site of nearly every major American speed record. It completed its first flight in the spring of 2025, and follow-on flights validated the aerodynamics, control systems, and fuel architecture the company had modeled on computers. Its job was narrow but essential. Prove that an airframe shaped for high-speed flight could still take off and land on an ordinary runway with conventional landing gear. The next aircraft in the line, roughly the size of an F-16 and powered by that same Pratt & Whitney F100 engine, first flew from Spaceport America in New Mexico in March 2026, operating over restricted airspace above the White Sands Missile Range. Just under 3 months later, on its third test flight, it broke the sound barrier, reaching a recorded speed of roughly Mach 1.21, a milestone the company has publicly described as the first time a privately funded, uncrewed jet has been confirmed to fly supersonic. It remains, by the company's own description, a low supersonic demonstrator rather than a hypersonic aircraft. But the significance isn't really about that top speed. It's about the pace. From a non-flying mock-up to a confirmed supersonic flight in roughly 2.5 years, with additional aircraft in the same family already being built to push further into the high supersonic range. Those next variants are meant to progressively expand the flight envelope before a later aircraft in the series attempts something no reusable aircraft has ever done in flight, switching live, mid-air, from turbine power to ramjet power, while carrying the full combined cycle engine. None of this matters unless it translates into something useful, and Hermes has been explicit about the 2 directions it's aiming for. One is a reusable, high-speed, unmanned aircraft intended purely for defense missions. Something that can sprint across a contested body of water in well under an hour, gather intelligence or jam enemy sensors, and return to base to fly again, rather than being expended like a missile. Defense planners have talked publicly for years about wanting exactly this kind of capability, fast enough that existing air defenses struggle to intercept it, and reusable enough that it isn't a one-time asset. Current hypersonic weapon systems, fielded by other major powers, including maneuvering glide vehicles that skip along the upper atmosphere and change course mid-flight, have already made clear that traditional missile defense, built around predictable arcing trajectories, is not well suited to this new category of threat. A reusable high-speed aircraft on the American side is meant to close a different kind of gap, not defending against the threat, but restoring the ability to respond and return. The other direction is civilian and considerably more ambitious for the average traveler. A small, roughly 20-seat passenger jet aimed at cruising near Mach 5 on long overwater routes, cutting a flight from New York to Paris down to somewhere around 90 minutes. It's worth being honest about the obstacles here. A rule dating back to 1973 bars routine supersonic flight over the continental United States because of sonic booms, which means any hypersonic airliner would likely be restricted to ocean routes unless that regulation changes. NASA and Lockheed Martin have been testing an experimental aircraft specifically designed to soften a sonic boom into something closer to a distant thump. And if that research eventually persuades regulators to loosen the rules, it could open the door for a hypersonic airliner to fly more freely. Until then, the commercial version of this technology stays largely over water. Hermeus isn't working alone in this space. Other companies have flown reusable, rocket-powered test vehicles past Mach 5 using a very different approach, dropping the aircraft from a carrier plane and igniting a rocket engine mid-air rather than taking off under its own power. A separate supersonic airliner project has already broken the sound barrier in test flights of its own prototype. And a well-funded European engine program spent decades developing a similarly ambitious combined cycle concept with its own pre-cooling technology, only to run out of money and enter bankruptcy before its engine ever left the ground. What sets the American program apart at this point isn't a finished aircraft. It's flying hardware, a funded partnership with the U.S. Air Force, and a steady cadence of real test flights generating real data rather than years of simulation.